Welcome back. We've been looking at Lewis dot structures, and we know that Lewis dot structures are flat and molecules are three-dimensional. So what we're getting ready to do now is make our first leap into 3D. And our first leap into 3D is with the theory called VSEPR for short, V-S-E-P-R. VSEPR stands for valence shell electron pair repulsion theory. Okay? Now, VSEPR is one of those theories that came about from experimental observation. All theories should come from experimental observation. They were looking at the three-dimensional structure of water using X-ray crystallography. Now, let's draw the Lewis dot structure of water and let's talk about it here for a second. Okay? So if we look at water, H2O, dihydrogen monoxide, if we were using the systematic naming system, we have two hydrogens at 1 electron apiece. There's one oxygen at 6 electrons, so that's 8 electrons. Okay, oxygen's going to go in the middle, hydrogen, hydrogen, 2, 4. 4 electrons left, so 2, 4. Minus 4, 0 electrons left. Here's the Lewis dot structure of of water. Oxygen has 2 lone pairs and has 2 bonds. When they looked at the Lewis dot structure, they predicted that this molecule was going to be linear, meaning that all the atoms were going to end up in a straight line. Okay? When they did the X-ray crystallography, they got something like this with a bond angle of 104.5 degrees. It's not in a straight line. And they had to look at this and they had to say, why? Why is this guy not linear? And the explanation they came up with had to do with the fact that there were lone pairs in the valence of the oxygen, the central atom. And what they've said is that electron groups, okay, in the valence around a central atom repel each other. Okay, that's where the repulsion comes from. And you want to have the maximum separation between electron groups to minimize the electron-electron pair repulsion. And the furthest that these electron groups can get away, the further these electron groups can get away from each other, the better. All right? So let's go over here for a second. All right. So valence shell electron pair repulsion theory. Electron groups around a central atom, the atom that is between at least 2 other atoms, are arranged in such a way as to get maximum separation between the electron groups so as to minimize electron pair repulsions. Now, let's talk about electron groups. I'm going to use some language here that we haven't seen before. An electron group is either a lone pair or a bond in the valence of the central atom. A bond could be a single bond, a double bond, or a triple bond. Remember that if I build a double bond, I'm making 2 connections between the same 2 atoms. So those bonds, the first bond and the second bond between 2 atoms, they're parallel with each other. And the same thing, if I make a triple bond, that third bond between the 2 atoms is parallel with the other 2. So they occupy one region in 3D space. A lone pair, or a pair of electrons in an atom's valence, that are not, is a pair of electrons in an atom's valence not involved in bonding. Okay? We only look at these on the central atom. There could be lone pairs on the edge atoms, but they don't count in VSEPR. We're only looking at the lone pairs on the central atom. Okay? So an electron group is a lone pair or bond to the central atom. Lone pairs are pairs of electrons not involved in bonding. Again, we're looking only at the central atom. Then we're going to use the term bond group, okay, or bond. It's a bond between two atoms. A single bond, double bond, or a triple bond counts as a single bond group. Okay, and again, I'm going to reinforce, we're only looking at what's going on around a central atom. So, the central atom is the atom that's bonded to at least two other atoms, and the bonds and lone pairs in the central atoms decide the shape around that atom. Now, I keep emphasizing this because a lot of people, when they get ready to play with Vespers, start looking at all of the lone pairs, even those on the outer atoms. We're only going to look at the central atom. And just like with doing Lewis dot structures, for the most part, we're going to stick to cases where we're working with a single central atom. Okay? So if we look at the number of possible electron groups around a central atom, we have 5 choices. We could have 2 electron groups, 3 electron groups, 4 electron groups, 5 electron groups, or 6 electron groups. The maximum number of electron groups you can have around a central atom is 6. And it starts to get really crowded. Okay? Now, each is associated with a specific electron group arrangement. An electron group arrangement is sometimes also called electron group geometry. It's the geometrical arrangement of the electron groups around the central atom that leads to the minimum energy for the system and the maximum spacing for electron groups around the central atom. So let's look at what the names are for the 5 electron group arrangements. 2 electron groups is called linear, 3 electron groups trigonal planar, 4 electron groups tetrahedral, 5 electron groups trigonal bipyramidal, and 6 electron groups octahedral. Now, let's look at some pretty pictures. Okay? Essentially, we can use balloons to represent electron groups. Buy some balloons and try this at home. Okay, if you try 2 balloons together, where they're tied together can represent where the central atom is. And the furthest those balloons can be apart is on opposite sides of the central atom. 2 electron groups. We're going to go through and I'm going to give you examples of each. If we have 3 electron groups, if you try 3 balloons together, you'll discover that they'll make a triangle in a plane. Okay, central atoms, again, where the knot is. If you have 4 electron groups, this is the first time we move away from a planar structure, everything in the plane, to getting something that really looks 3D to us. This is tetrahedral. There are 4 electron groups. You tie 4 balloons together, they're going to give you this shape. Think about the central atom being in the middle of a 3-sided pyramid. Well, a 4-sided pyramid. We've got a base and 3 top sides. Okay? So there's the base, and there's the top of the pyramid. And the central atom is in the center of the pyramid. Okay? Trigonal bipyramidal. Okay, we have 3 atoms in the plane that the central atom is in. You can think about those as being at an equator position. And then you have a balloon up and a balloon down. Up and down. Okay? So there is a 3-sided pyramid pointing up, a 3-sided pyramid going down, and their bases are stuck together. Last is octahedral. You end up with 4 electron groups at the equator position, and 1 at the North Pole and 1 at the South Pole. So you have 2 4-sided pyramids stuck base to base. Okay? Octahedral because it's an 8-sided object. All right. Now, Within each possible electron group arrangement, okay, there are different molecular shapes or molecular geometries, which is the arrangement of the atoms in the molecules relative to each other. Now, this has to do with the fact that some of those electron groups can be lone pairs and not bonds. Okay? So we're going to have not only electron group geometries or electron group arrangements, we're going to have molecular shapes or molecular geometries. Okay? Let's look at each electron group arrangement and look at the possible molecular shapes. Now, the last thing I want to define for you before we go into running the list is to define bond angle. It's the angle formed between the nuclei and two atoms connected to the central atom. Okay? All right, here's table 5.5 from your textbook. This is a very important table. Okay? So we're going to run through this table. Now, I'm going to go grab a model because we're going to need some models. I'll be back in just a second and we'll pick up right here. Here we go. Now, when we have two electron groups, both of them are bonds. We have 0 lone pairs. The molecular geometry is linear. Okay? The bond angle is 180 degrees. So if we look here, from this bond to this bond, they're on opposite sides of the central atom. That is 180 degrees. An example would be something like carbon dioxide. You can see it's drawn there. It's got the double bond. Okay, so there's just two bonds to the central atom, a double bond on this side, a double bond on this side. So, linear. Now, there's only one option when I have two electron groups. Let's move on to look at 3 electron groups. Okay? When we have 3 electron groups, we have 3 bonds and 0 lone pairs. Okay, the electron group arrangement is trigonal planar. So you can see here, all of these atoms are in a plane. Trigonal planar. And that's because these outer atoms form a triangle. The bond angles here are 120 degrees. Now notice when they wrote out the Lewis dot structure, it doesn't show that trigonal planar shape, but it does show that there are 3 atoms attached to the central atom. If we were to draw a kind of ball and stick model like you can do in a computer, okay, to represent this, you can see they draw it trigonal planar. When we have 3 electron groups, we have a second option, and the second option is when I have 2 bonds and 1 lone pair. We have this. Okay? I like it like this. Mickey Mouse ears. Mickey Mouse head. Alright. Now, the bond angle here is approximately 120 degrees. Turns out that a lone pair of electrons, because those electrons are only having to pay attention to the central atom, actually bulge out a little bit. The electrons in the bonds, okay, here, the connection, they run a much tighter area in space because they're running back and forth between 2 atoms. These get a little lazy and kind of group, kind of spread out. So what happens here is this bond angle, the bond between these 2 bonds actually get squeezed a little bit closer together. So the bond is going to be a little bit less than 120 degrees. Sulfur dioxide is an example here. Ozone would be an example. It's going to look like this. And notice that double bond could be there or there. This is one of the 2 resonance structures for sulfur dioxide. Okay? We talked about resonance, just kind of reminding you. And we get something that looks like this. Now let's go on to 4 electron groups. Okay? When we have 4 electron groups, I could have 4 bonds and 0 lone pairs. Its electron group geometry, or electron geometry, is tetrahedral. Looks like this. Okay, nice tetrahedral shape. Its molecular geometry is also tetrahedral because those are all bonds. The bond angle here is 109.5 degrees. CH4 is our common example. CH4 is an organic molecule called methane. No, you don't have to have that memorized. Don't panic. Okay? And it looks in 3D like this. And with their fancy computer, they can do nice 3D looking drawings. Okay? Looks like this. Now, if I swap out a bond for a lone pair, I have 4 electron groups still, 1, 2, 3, 4, but 3 of them are bonds, 1 is a lone pair. I still have an electron group geometry of tetrahedral. There's still 4 electron groups. But my molecular geometry is different because all that we see when we do X-ray crystallography is this atom, this atom, this atom, and this atom. All we see is the nucleus and the position of the nuclei relative to each other. So we get this. This is kind of open space up here, but when we take a picture, we don't see anything. It's kind of like maybe plexiglass. The light goes through. Okay? So we get this kind of shape. So we get the external atoms to form a triangle as a base, and you can kind of think of this lone pair as being sitting up here as a nice beacon light on top. Central atom is sitting a little bit above it, so it forms a triangular based pyramid. Okay? So it's called trigonal pyramidal. The bond angle is going to be a little bit less than 109.5. Classic example of this is ammonia. And you can see when you draw the ball and stick diagram, that top space is not showing anything because there's not a bond there. But the lone pair is holding it open. Lastly, okay, we can have 4 electron groups with 2 bonds and 2 lone pairs. The electron group arrangement is still tetrahedral. But we now call the geometry bent, the molecular geometry bent, because if you look at it, the central atom and the 2 external atoms, they form kind of a V. It's not a straight line anymore. The bond angle here is really squeezed down. It's quite a bit less than 109.5 degrees. Water, which started us down this road, is our classic example here. So 2 lone pairs, 2 bonds, okay? And it gives us this bent shape. So they're drawing it like this. Now notice that all those atoms end up being in a plane, okay? Lone pair here, lone pair here. So it looks like, you know, if you're drawing it on a piece of paper, it looks kind of flat like that. All right, so that's 5 electron groups. Now we can move up to 4 electron groups. We're going to move up to 5 electron groups. Okay. Here is 5 electron groups. I'm going to kind of turn it like that. So 1, 2, 3, 4, 5. Let me scroll up the screen. So at 5 electron groups, all 5 of them bonds, no lone pairs, we call this trigonal bipyramidal. And since everything's a bond, the molecular geometry is trigonal bipyramidal. And we've got two different bond angles. From the equator down to, the pole to equator is 90 degrees. But along the equator, the electron groups are 120 degrees apart. So your book refers to it as equatorial, around the equator, 120, and axial, 90. I would have said polar 90, but they say axial. Okay? So phosphorus penta 5 chlorines. So phosphorus pentachloride is our example here. And there's a pretty ball and stick drawing. If we have now one lone pair, 4 bonds and 1 lone pair, I got to decide where the lone pair is going to go. Okay, and the lone pair is going to want to go where it has the most room. Now we would be tempted to say a polar position, but we'd be wrong. Because if you look at the pole, it's it's 90 degrees from all of its nearest neighbors. But if you're on one of the equator positions, you got 90 degrees here and here, but you got 120 and 120 here. There's actually more room here at the equator. So when we have a lone pair on a trigonal bipyramidal electron group arrangement, it goes at the equator. And we get a shape that looks like this. Okay? Now why am I holding it this way? Because, okay, this explains the molecular geometry name. Now guys, I'm gonna kind of stand back here a sec, hold this for you. So if we look at this guy, look, it goes seesaw. Okay? That's where the name comes from. It's seesaw. Now, this is going to stay at 120 degrees. Well, it might squeeze down a little bit more. This might be a little bit less than 90. It squeezes it a little bit. Sulfur tetrafluoride is an example. We've got 4 bonds and 1 lone pair. So if we go to having 3 bonds and 2 lone pairs, 3 and 2, notice, add up to 5, I get this. Okay? The electron group geometry is still trigonal bipyramidal, but its molecular geometry is T-shaped. Okay? Now, there are no bonds here. So the only bonds I have are here and here, here and here. So the bond angle to the nearest bond here is 90 degrees. So 90 degrees here, 90 degrees here. Bromine trifluoride is our example here, and there's your nice stick model. Lastly, we can have only 2 bonds and 3 lone pairs. Again, the lone pair goes at an equator position. We get this. Okay? It's still trigonal bipyramidal. It's an electron group arrangement, but its molecular geometry is called linear because all of the atoms are in line. And bond to bond is 180 degrees. Xenon difluoride is a perfect example. Notice 3 lone pairs, 2 bonds. Okay? Now I want to reinforce to you guys that these 2 numbers, the number of bonds, the number of lone pairs, always have to add up to the number of electron groups. Okay? Now, one last option, and that's if we have 6 electron groups. Okay, here's 6 electron groups. Now I'm going to turn it this way a little bit and tilt it so that you can kind of see everything. Okay, so I've got an electron group up here at the North Pole, electron group here at the South Pole, and 4 electron groups at the equator. Now, 90 degrees here, 90 degrees here. Everything is 90 degrees from its nearest bond or electron group neighbor. Okay? So this is called octahedral because it makes an 8-sided object. I think of it often as a square, 2 square pyramids base to base. Okay? Sulfur hexafluoride is our example, and there's a pretty ball and stick modeled. And we're going to look at a couple of options here. We've looked at all 6 being bonds. Now let's look at having one lone pair. Okay? When I take away one of the electron groups, it doesn't matter which one, well, one of the bonds and make it a lone pair. Doesn't matter which one I do, it's all going to look the same. So if I took that one out, okay? If I took this one out and turned it that way, it looks the same. So we have 5 bonds, one lone pair. Its electron group arrangement is still octahedral. There are still 6 electron groups around the central atom. But now we call it square pyramidal. It's a square pyramid. Okay? Bromine pentafluoride is in our example here. So notice all of these guys in the central atom are in the same plane, and then I have one sticking above the plane. Okay? When we have 6 electron groups, the lone pairs want to be opposite each other. So think about putting them at the north and south pole. We leave all the bonds at the equator. Okay? Bond angle still 90 degrees. And now I have a square in a plane with the central atom being in the center of the square. Xenon tetra fluoride is our example. And here's a nice kind of look at it. Okay? Now, I'm going to draw some Lewis dot structures over here, and we're going to see if, we're going to just kind of talk through some examples to make sure we're all doing okay with this. Just give you some more examples. We're going to be doing this in lab. Well, actually, since we're going to do this in lab, I'm not going to worry about that. I'll have plenty of time to do lots of stuff with you in lab. So let's look at representing molecular geometry on paper. Okay? Now, if we're going to represent molecular geometry on paper, we're going to use straight lines to indicate bonds or electron groups in the plane of the paper. We're going to use hashed wedges for bonds or electron groups that are going into the page, so going behind the page, and solid wedges for bonds or electron groups that are coming out of the page. Now here's a good reference for you. Roll this up just a little. Maybe just shrink this down one. Try to get everything I'm trying to get into the page. Okay, I think I got it all in now. Okay, guys, this is a good reference for you for drawing. On test 3 here, there are going to be some examples where I'm going to give you a Lewis dot structure, and I'm going to ask you to draw its electron group arrangement and its molecular geometry in 3D. Okay? So let me show you some examples. Now, if I start out simple with something like carbon dioxide, I have 2 electron groups. This is linear. So I'd write carbon, line oxygen, line oxygen. This is its electron group geometry, and it's also its molecular geometry. Okay? Now, if I go to something like boron trifluoride, okay, it's trigonal planar. Again, everything's in a plane. So boron, fluorine, fluorine. I don't show the lone pairs on anything, I'm just showing the position of the atoms relative to each other. This is its electron group geometry, and its molecular geometry is going to look exactly the same. If I have something like ozone, looks like this. There are still 1, 2, 3 electron groups. So it's still trigonal planar. So here I have a lone pair of electrons, there I have an oxygen, there I have an oxygen. That's its electron group arrangement. Its molecular geometry looks like that. Let me make sure you can see. Yes. Okay? Now, when we have 4 electron groups, that's when I get to start using wedges. I'm going to look at CH4, ammonia, NH3, and water, H2O. Okay, the Lewis dot structure for methane looks like this. There are 4 electron groups. So carbon, hydrogen, hydrogen. I'm going to put a solid wedge here for our hydrogen, and a dashed wedge there for a hydrogen. Okay, this would be its electron group geometry. Its molecular geometry is going to look exactly the same because everything is a bond. Now on ammonia, the Lewis dot symbol looks like, the Lewis dot structure looks like that. So nitrogen, I'm going to put a lone pair there, hydrogen, hydrogen, hydrogen. To draw its molecular geometry, I'm just going to leave off the lone pair. Looks like that. Water, if we draw the Lewis dot structure, it's going to look like that. Okay. Now, I'm going to put the 2 hydrogens in the plane of the board because it's going to make it easier when I draw the molecular geometry. You don't have to put them there. I have a lone pair of electrons here. I have a lone pair there. So when I drop them off, I just get that. Okay, 4 electron groups. All right. Now let's go with 5 electron groups. Let me think of my examples with 5 electron groups. Okay, we're going to use phosphorus pentafluoride. And then I'm going to use sulfur tetrafluoride. And then I'll use bromine trifluoride. And then we'll use xenon difluoride. Okay, when I draw the Lewis dot structure here, lots of dots. Okay, I look at the central atom, the phosphorus, it's making 5 bonds. Okay, so I'm going to go 1 up, 1 down, 1 in the plane of the board, 1 here that's sitting out in front, 1 that's going behind. Okay, the molecular geometry is going to be identical because everything's a bond. When I get to sulfur tetrafluoride, S, F, 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 lots of dots. There's still 5 electron groups, but one of the electron groups is a lone pair. Okay, so sulfur, fluorine, fluorine. I'm going to put the lone pair over here. It's got to be in one of the equator positions. So, you know, I could have also drawn it here, but I like it there. Old habits die hard. That's what its electron group geometry would look like. Its molecular geometry is just the same thing. I just don't draw the lone pair in. And if you laid that this way, you could see that seesaw shape. Okay? So this is trigonal bipyramidal seesaw. Okay, when I get to bromine trifluoride, looks like this. 5 electron groups, 3 bonds, 2 lone pairs. Okay? So bromine there, I'm going to put a fluorine here, fluorine here, fluorine here. I do that because all of these atoms end up in a plane. Lone pair of electrons there, lone pair of electrons there. So when I draw this electron group arrangement, I show the lone pairs. In the molecular geometry, I don't. This is T-shaped. So electron group arrangement, molecular geometry. Last one is xenon difluoride. Looks like that. So Xe, F, F, lone pair of electrons here, lone pair here, lone pair there, and the molecular geometry is linear, and you can see all of the atoms are in a straight line. Okay? All right, now, lastly, 6 electron groups. Okay, when we have 6 electron groups, it's octahedral. So the electron group arrangement is always going to be octahedral. We're going to be looking at 3 options here. We're going to be looking at all of them being bonds, having 1 lone pair, and then having 2 lone pairs. So sulfur hexafluoride, SF6, sulfur, fluorine, 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 fluorine. Looks like that. Sulfur hexafluoride. That's its Lewis dot structure. So I'm going to go fluorine, fluorine, wedge forward here, wedge backwards, wedge forward here, wedge backwards. So that's our octahedral molecular geometry, and our electron group arrangement. Our molecular geometry looks exactly the same. Okay. Electron group geometry, molecular geometry. Now we're going to go with having 1 lone pair. So bromine pentafluoride would be our example. Okay, so the electron group geometry, I'll have fluorine here, a wedge coming out here with a fluorine, a wedge going back with a fluorine, a wedge coming out with a fluorine, a wedge going back with a fluorine, and I'm going to put my lone pair there because it's molecular electron group arrangement is octahedral, but its molecular geometry is square pyramidal. So bromine, fluorine, wedge forward fluorine, wedge back fluorine, wedge forward fluorine, wedge back fluorine. Okay? Our last one is if I have 2 lone pairs and 4 bonds. So xenon tetrafluoride is our example. There's the Lewis dot structure. So I've got xenon, I'm going to put my lone pairs here and here because they're on opposite sides. Okay? They want to be as far apart from each other as possible. So I'm going to have a wedge in front with the fluorine, a wedge going back with the fluorine, wedge going forward with the fluorine, wedge going back with the fluorine. Now, this is the electron group geometry, or your book just calls it the electron geometry. Okay? Now, when I get ready to draw the molecular geometry, there are 2 ways you see this done. It's done like this, and the lone pairs are in front of the plane and behind the plane directly. Or you can do it using the wedges. the square planar. This is probably the easier way to draw it, but if this helps you because you're just taking off the lone pairs from up here, draw it this way. Either way is acceptable. And yes, we're going to be doing this in lab where I'm going to be standing over, I'm going to be talking you through things. But being able to draw like this starts to help reinforce the three-dimensional nature of the molecules we're dealing with. And that three-dimensional nature is important. Okay? Now, why would that three-dimensional nature be important? Well, it's going to help us understand how that molecule is going to behave. Okay, how it's going to interact with other molecules, and it's going to control its physical properties, and in some ways it affects how it can chemically react because it tells us what bonds are exposed and what lone pairs of electrons are hanging where. Okay, now let's look at the screen here for a second. And let's look at this organic molecule. Okay, this is a slightly bigger molecule. It's got 4 internal or interior atoms. They're atoms that are between at least 2 other atoms. So this nitrogen has 3 atoms attached to it. This one has 4. This one has 3. This one has 2. That's what makes them internal atoms.